Okay, so thanks everybody for coming back. So we're now happy to have the last talk of today by Jason Schweinsberg on Yaglom-type limit theorems for branching Brownian motion with absorption. And let me just recall you that after the talk, there is going to be a poster session in the poster room north of the main hall. And also yesterday's slide, so the videos of yesterday's talks have been put up to the YouTube channel, so feel free to have a look there. Okay, thanks Jason for coming.
Okay, thank you, and thanks for the invitation to speak here. I'm going to talk about some Yaglom-type limit theorems for branching Brownian motion with absorption. This is based on joint work with Pascal Maillard, and I want to acknowledge also that some of the tools that we used originated in earlier work with Julian and Nathaniel Barasticki. So first, I want to define branching Brownian motion with absorption. We begin with some configuration of particles located on the positive real line. Each particle independently moves according to standard one-dimensional Brownian motion with a drift to the left of mu. For simplicity, we'll say that each particle splits into two particles at rate 1/2, although the results can be extended to cover more general supercritical offspring distributions. And particles are killed if they reach the origin. So here's a picture of the process created by my graduate student Jiaqi Liu. In this example, we begin with just a single red particle. It moves according to standard Brownian motion with drift for an exponentially distributed time, and then it splits into two particles, one red and one blue. Then those particles move according to independent one-dimensional Brownian motions with drift until they divide, and so on. And here we can see that the blue particle reached the origin and was killed, but we also have some particles that are still alive at the end of the picture. Now, perhaps the most basic question that one can ask about branching Brownian motion with absorption is whether it eventually dies out or whether some particles survive forever. Harry Keston answered this question way back in 1978. Keston showed that if the drift to the left is greater than or equal to 1, so that particles are drifting rapidly towards the origin, then the process dies out with probability 1. However, if the drift is strictly less than 1, then the process survives forever with positive probability. For the rest of the talk, we're going to assume that mu is equal to 1, so that we're in the case of critical drift. Now we're going to focus on two questions. First, we know the process will eventually go extinct, but we want to know what is the probability that the process will survive for an unusually large time t. And second, conditional on the event that the process survives for an unusually large time t, we want to understand what the configuration of particles looks like at time t. Results like this are known as Yaglom-type limit theorems. Now, although we will only consider mu equal to 1 in this talk, I want to mention that John Harris and Simon Harris obtained some results in this direction for the subcritical case in 2007, and my graduate student Jiaqi Liu has some new results for the case where the drift is just slightly supercritical, just slightly subcritical rather. So now I want to state what I consider to be the main results, although I will state stronger versions of these results as well as some additional results later on. So we'll let n of t be the number of particles in the system at time t. We'll let zeta be the time when the process goes extinct, and c is defined to be this constant, the cube root of 3 pi squared over 2. Now, Keston showed in 1978 that if we start the branching Brownian motion from a single particle at x, then for sufficiently large times t, the probability that the process survives for at least time t is bounded above and below by these two quantities. So the survival probability looks a lot like e to the power, or x times e to the power x minus ct to the 1/3, but the upper and lower bounds here differ by more than a constant factor because of these factors of e to the plus or minus log t squared. So here is the new result which is sharper. If we start with a single particle at x, then the probability that some particles survive until at least time t is asymptotically a constant times x times e to the power x minus ct to the 1/3. And here this symbol means that the ratio of the two sides tends to 1 as t tends to infinity. Derrida and Simon had obtained this result more than 10 years earlier using non-rigorous methods. Also in 2014, in joint work with Julian and Nathaniel Beresticki, we obtained upper and lower bounds on this survival probability that were correct up to multiplicative constants. Now we also have a Yaglom-type limit theorem for the process conditioned on survival until a large time t. As before, n of t is the number of particles at time t, and we'll let r of t be the position of the rightmost particle at time t. That is, the particle that's farthest away from the origin. So then Keston showed that if we start with one particle at x, and we condition on the survival of the process until time t, then the probability that the number of particles at time t exceeds e to the k1 times t to the 2/9 times log t to the 2/3 tends to 0 as t goes to infinity. And likewise, it's asymptotically unlikely that there's any particle located at a distance more than a constant times t to the 2/9 times log t to the 2/3 away from the origin. So we're now able to obtain a sharper result, which tells us that the log t to the 2/3 factors are unnecessary. The log of the number of particles at time t is of the order t to the 2/9. More precisely, when we start with one particle at x and conditional on survival until time t, t to the minus 2/9 times the log of the number of particles at time t converges in distribution to the cube root of an exponential random variable as t goes to infinity. And likewise, t to the minus 2/9 times the position of the rightmost particle at time t converges in distribution to the cube root of an exponential random variable. So those are the main results. I now want to describe some of the tools that we need to put together to prove these results. One thing that we'll need to do is to calculate moments. And an important tool for calculating moments, first moments, is known as the many-to-one lemma. So we'll let qt of xy be the density for this process, which means that the expected number of particles in some set A at time t is given by integrating qt of xy over the set A. And because particles are branching at rate 1/2, we can write qt of xy as e to the power t over 2 times pt of xy, where pt of xy is the density for the position at time t of a single Brownian particle started at x with a drift of -1 and absorption at 0. So we can calculate expectations involving branching Brownian motion just from knowing the density of a single Brownian particle. There's also a more complicated formula for computing second moments using this density q, which is useful for controlling the fluctuations of the process. However, the problem that we encounter is that the moments don't capture the typical behavior of the process. The expected number of particles alive at time t is dominated by rare events in which one particle moves unusually far to the right and then has a huge number of surviving descendants that avoid the barrier at 0. So the expected number of particles is much greater than the number of particles in a typical realization of the process. To understand the more typical behavior, we therefore need to do some truncation where we kill particles that get too far away from the origin. Now, one way of doing truncation is to choose some positive number L and kill particles both at 0 and at L. If we do this, then using the many-to-one lemma, we can get this approximate formula here for the density of the process at large times. Now notice the formula is proportional to e to the x times the sine of pi x over L. So if there's a particle at x then the number of descendants of this particle alive at future times is roughly proportional to e to the x times the sine of pi x over L. Also, the formula is proportional to e to the minus y times the sine of pi y over L. So once the process has had time to reach a sort of equilibrium, the particles end up in a configuration in which the density of particles near y is going to be roughly proportional to e to the minus y times the sine of pi y over L. Now, if we put down e to the L particles according to this density, then the rightmost particle will typically end up near L. And so if the particles have settled into an equilibrium configuration, and if the right boundary has been set to be near the location of the rightmost particle, then the log of the number of particles should be approximately the position of the rightmost particle. Notice here, though, that the number of particles is decaying exponentially at rate pi squared over 2L squared as the process moves towards eventual extinction. And so to keep the position of the right boundary close to the logarithm of the total number of particles, we need to move the right boundary closer to the origin over time. And you can solve a differential equation to figure out what the appropriate right boundary should be. And if we're given a positive number t, which we think of as being the amount of time for which we expect the process to survive, then we set the position of the right boundary to be Lt of s, which is c times t minus s to the 1/3 power. So roughly speaking, if a particle gets close to Lt of s at time s, then it has a good chance to have a descendant alive in the population at time t. And results of Matt Roberts, which build on earlier work of Novikov, then allow us to get an approximate formula for the density, even when the right boundary is moving over time. And because our right boundary is moving very slowly, the density formula resembles very much this density formula for branching Brownian motion in a strip. Now, when we do truncation, we hope that with high probability no particles are killed, so that the truncated process behaves the same as the original process. We also hope that the truncation causes the variance of quantities of interest to be small relative to the square of the mean, so that we get law of large numbers type behavior and the fluctuations are well controlled. Unfortunately, we can't quite do this here. So suppose we kill particles at Lt of s plus a, where a is some constant. Then as a tends to minus infinity, the variance of the number of particles does get small relative to the square of the mean. However, the number of particles killed at the boundary gets large. On the other hand, if we choose a to be a large positive number, then the number of particles killed at the boundary does tend to 0, but the variance of the number of surviving particles gets large relative to the square of the expectation. So we need another approach to truncation. And what we'll do is to stop particles when they reach Lt of s minus a, where a is a large positive number. So this gives us good control over the particles that do not reach the boundary. But when a particle hits the right boundary, instead of killing the particle, we'll follow the descendants of the particle until they reach Lt of s minus a minus y, where y is another large constant. And then we'll reincorporate these descendants back into the process. Now let's let m of y be the number of descendants of the particle that reach Lt of s minus a minus y. Navarre showed in 1987 that as y goes to infinity, y times e to the minus y times m of y converges almost surely to a limiting random variable w. And later it was shown that as x goes to infinity, the probability that w is greater than x is asymptotically 1 over x. So now we can put these pieces together to establish a useful limit theorem. So we can let x1 of s, x2 of s, and so on be the positions of the particles at time s. And now for any positive number t, one can define for s between 0 and t, this quantity zt of s. And this turns out to be a natural measure of the size of the process at time s. Notice we're taking a sum over all particles at time s, and the contribution from a particle at the location x is proportional to e to the x times the sine of pi x over the position of the right boundary at time s. And that's coming from the density formula for branching Brownian motion in a strip. So now as t goes to infinity, under suitable initial conditions, these processes zt will converge to a limit, and the limit will be a process with jumps. The particles that stay below the right boundary will behave in a very predictable way, but random jumps will occur when one particle drifts unusually far to the right and hits the boundary at LT of s minus a. When that happens, many descendants of this particle can survive, leading to a sudden increase in the total number of particles. Now, the size of the jump is proportional to the random variable w on the previous slide. So from the tail behavior of w, we see that the process makes jumps of size greater than x at a rate proportional to 1 over x. Also, the jump rate is proportional to the likelihood that a particle reaches the right boundary, which is proportional to the size of the process, zt of s. And combining these two observations, we see that the limit process should be a so-called continuous state branching process of the form studied by Neveu, where the branching mechanism is given by a times q plus b times q log q. So this leads to the following limit theorem. We assume that zt of 0, that's our measure of the size of the process at time 0, converges in distribution to some random variable z as t goes to infinity. And we assume that LT of 0 minus R of 0 converges in probability to infinity, which means that the rightmost particle at time 0 is starting far away from the right boundary at LT of 0. And then the finite dimensional distributions of these processes zt converge as t goes to infinity to the finite dimensional distributions of a continuous state branching process with branching mechanism a times q plus 2/3 times q log q, where a here is some constant whose value we actually don't know. Now notice there's a time change here, which maps the interval from 0 to t onto the positive real line. So the behavior of the branching Brownian motion close to time t is linked to the behavior of the continuous state branching process at very large times. And I should mention that a similar convergence result appeared in my earlier paper with Julian and Nathaniel Beresticky in the case when the drift is just slightly supercritical. So now let's let capital X be a continuous state branching process started at little x with branching mechanism a times q plus 2/3 q log q. Gray showed that if we let alpha be e to the minus 3a over 2, then this process approaches infinity with probability 1 minus e to the minus alpha x and approaches 0 with probability e to the minus alpha x. And the way we can think about this result is that at time 0, the population will include a certain number of so-called prolific individuals whose number of descendants at time u will tend to infinity as u tends to infinity. And the number of these prolific individuals has a Poisson distribution with a mean of alpha times x, which leads to these probabilities. And because of the result on the previous slide, the survival of the branching Brownian motion until time t roughly corresponds to the event that this continuous state branching process tends to infinity. So this connection gives us our theorem on the survival probability for branching Brownian motion. So we'll assume for simplicity that the initial configuration of particles at time 0 is deterministic, but the initial configuration of particles may depend on the parameter t. And recall here that zeta denotes the extinction time. Now, if zt of 0, that's our measure of the size of the process at time 0, converges as t goes to infinity to z, and if no particles start out too close to Lt of 0, then the probability that the process survives for at least time t converges to 1 minus e to the minus alpha times z. So that's coming from the corresponding result for continuous state branching processes. If zt of 0 converges to 0, and if no particles start out too close to Lt of 0, then we can approximate 1 minus e to the minus alpha z by alpha times z to get that the survival probability is asymptotically alpha times zt of 0. A special case of this result is when the initial configuration just consists of one particle located at x, and then the probability of survival until time t is asymptotically alpha pi times x times e to the x minus Lt of 0, and that's the result that we stated at the beginning of the talk. Now, as a corollary of this result, we can obtain the asymptotic distribution of the survival time for branching Brownian motion, conditioned on the process surviving for an unusually large time t. So we assume that as zt of 0, we assume that zt of 0 goes to 0, so that survival until time t is unlikely. And then this result says that conditional on the unlikely event of survival until time t, the amount of time past time t for which the process survives is of the order t to the 2/3, and furthermore, t to the minus 2/3 times zeta minus t converges in distribution to an exponential random variable. And the proof is simple enough that I chose to sketch it here. Let's find the probability of survival until time t plus y times t to the 2/3, conditional on survival until time t. So we can write this conditional probability as the ratio of these two probabilities. And then from the theorem on the previous slide, the numerator is asymptotically alpha times z sub t plus yt to the 2/3 of 0, and the denominator is asymptotically alpha times zt of 0. And then just from the formula for z, one can see that as long as no particle is too close to the right boundary, this ratio will converge to e to the minus cy over 3, which is why we get this exponential distribution with a mean of 3 over c. So now finally, we're ready to establish the Yaglom-type limit theorem concerning what the configuration of particles looks like at time t, conditional on the event that the branching Brownian motion survives past time t. Now, the key idea here is to think about what the configuration of particles should look like at time t if we know that the process is eventually going to die out at approximately time t plus s. So first of all, z sub t plus s of t should not be too large or too small. If this quantity is close to 0, then the process will most likely die out before time t plus s. If this quantity is very large, then the process will most likely survive well beyond time t plus s. Also, by time t, the particles should have had time to settle into a sort of equilibrium configuration. So from the formula for the density of branching Brownian motion in a strip, we see that the density of particles near y should be roughly proportional to e to the minus y times the sine of pi y over L sub t plus s of t. This means that the rightmost particle should be close to L sub t plus s of t, which is c times s to the 1/3 power. And from the relationship between the total number of particles and the location of the rightmost particle that we saw before, we see that the log of the number of particles at time t should be about the same, about c times s to the 1/3. So now, conditional on survival until time t, we know from the result on the previous slide that the process will survive approximately an additional t to the 2/3 times v time units, where v has this exponential distribution. So we can use t to the 2/3 power times v in place of s in these formulas. And then we see that the position of the rightmost particle at time t and the log of the number of particles at time t should both be approximately c times t to the 2/3 v to the 1/3 power, which is c times t to the 2/9 times v to the 1/3. And this leads to the following limit theorem, which was stated at the beginning of the talk in the case where we start with just one particle at x. So we assume here that zt of 0 is going to 0, so that survival until time t is unlikely, and the rightmost particle in the initial configuration is not too close to the right boundary. And then conditional on survival until time t, t to the minus 2/9 times the log of n of t, and t to the minus 2/9 times the position of the rightmost particle at time t, both converge in distribution to the cube root of an exponential random variable. And I'll stop here. Thank you.
Thank you so much, Jason. Are there any questions?
I've got one to get us started. So just on this last slide, you sort of, what your second bullet point says that the density of particles near y is proportional to this quantity.
Yeah.
That doesn't appear in the theorem. Is that right?
Well, it doesn't appear in the theorem that I chose to state here. We do have a different theorem that does describe more precisely what the density of the particles looks like. There are ways of making that kind of observation precise. But I chose to focus here on the Yaglom-type results for n of t and r of t.
Okay, thanks. Any more?
So I also have a follow-up question related to Matthew's question. So you're saying that you might have like Yaglom results related to the point process of view this process as like a point configuration, because right now it's like NT converges to something that we consider the point process.
Okay, so when you talk about the point process, I guess in the context of branching Brownian motion, I'm most familiar with the point process when we're discussing the details of the configuration near the rightmost particle. Is that what you have in mind here?
Well, you have a rightmost particle here. So
yes,
what in my mind is you just write the branching process as a point process, and if you view it as a marker process taking value in point measure, what is that possible to have some kind of like a Yaglom result on this space of point measures? Like
okay,
okay.
I understand now. Sorry. Yes. So what one can do is one can put a unit mass at the location of every particle, and then consider that as a random measure. If you normalize by the total number of particles, then you do get a limit, and basically what's going to happen is the limit density that you're going to see is going to be proportional to y times e to the minus y. So most of the particles are clustered close to the origin. If you want to focus on the particles that are actually going to have descendants surviving for the longest, you can do a kind of weighted point measure, where a particle at the location x is weighted by e to the x. And if you do that kind of point measure and normalize that, then you will see this something proportional to this sine curve showing up. So you can in fact see this density here in various ways by looking at the kind of point measure that you're referring to.
Oh, okay, thanks.
And maybe I can add that if you are interested in extremal particles there, then I would expect you get the same exponentially, well, the same point process as in branching Brownian motion without absorption, or more precisely as in the continuous random energy model, because this is the one which is closer in spirit to what we're doing here.
Thanks.
Okay, I think it's time. So thanks, Jason, again, and by clapping. So I'm switching off